am I audible now? Hello.
Yes, sir.
Okay. Okay. So basically, since there was no electricity in the campus, so that is why I have to start the late. Okay. Now the current has resumed, so I'm starting my class now. Okay. So in the last class we have discussed about the electric potential. Okay. So we discussed about the electric potential and how to represent the electric potential, and using a line charge, a point charge, line charge, or a surface charge. Okay, that we have seen. Okay, so electric potential we have seen that. Okay, which is a work done per unit charge. Okay. Okay, now the potential difference, we have also seen that if you have an electric field like this E and you have 2 points, point A and point B, you want to drag a point charge, okay, from point A to point B. So you are doing some work. Okay, so work per unit charge will give you the potential difference. Now potential difference is independent of the path. That means if you travel from A to B in this direction, or if you travel from a longer direction, whatever it is same. Okay, now if the potential difference from A to B is say VAB, okay, and the potential difference, that means if you are shifting a charge from point A to point B, then that is a potential difference. But if you are shifting the charge from point B to point A, again bringing it back, that is potential difference between B and A. So A and B and B and A both are actually equal but of opposite sign. That is why potential drop between VAB is between A and B is VAB, and between B and A is VBA. So VBA will be minus of VAB. That means if you take the potential difference along a closed path from A to B and again back to A, okay, so that will be actually equals to 0, because you add them, because along a closed path means the voltage, the potential difference between AB plus the potential difference between BA, that will be equals to 0, because both are actually equal and opposite. Okay, so that means since it was discussed that potential is nothing but Q by 4 pi epsilon naught R. Okay, this was potential. So basically the relationship between potential and electric field intensity is this. Okay, because it is like that if you want to see the definition, that electric field intensity is what? Force per unit charge. Okay, force per unit charge. And potential, what you are doing, you are actually, the equation is that it is Q by 4 pi epsilon naught R. That means if you see the difference of equations, if you see the equation of Coulomb's law, okay, that is Q1 Q2 4 pi epsilon naught R square, and for E it is Q1 by 4 pi epsilon naught R square, and for V it is Q1 4 pi epsilon naught R. R means the distance. Okay, because the work done to bring a unit positive charge. Okay, the work done to bring a unit positive charge from infinity to a particular point. Okay, that is the potential at that point. Suppose V1, so that is Q1, that means the potential due to Q1. Okay, so potential due to Q1 charge at a particular point, which means that if you have a space like this field and you have a Q1 charge, once again someone is trying to enter. Okay, that means you have a point charge Q1, okay, a point charge, and it is having electric field. Okay, so at this particular point, okay, it is having electric field E1. If you have 1 Coulomb charge outside, if you bring and put it over here, so what will happen? It will experience a force due to the effect of Q1 charge. Okay, it will experience a force that is equals to E1. Now the work done to bring this particular point charge from here to this point the work done is called potential. So that means that 1 coulomb charge, when it is placed at point P, suppose this is point P, which is a distance r from the charge, so it will experience a force that is equals to the electric field intensity E1, but the work done to bring it at this particular point, that is called the potential. So at point P there will be a potential of V1, okay, and at V1, at point P, the force is experienced as E1, but the potential is V1. So there is a relationship between V1 and E1. Okay, that means V1 means the potential is equals to the line integral of E dot dl, where line integral is from infinity to r. Okay, that we already seen. The minus sign is there. If you can see the minus sign. Okay, we have come across this equation from here. Okay, if you can remember, yesterday last class we have discussed the work done is force and displacement. Force is Q into E. So potential is actually work done by charge. So it is this one. So this is potential difference. So potential difference between, that means from A to B, what is the work done? That is the potential difference between A and B per unit charge. But potential difference at a particular point, that means it is a potential at a particular point. So potential at a particular point is not equals to potential difference, but it can be assumed to be the potential difference. That is how? That is potential difference from infinity, between infinity at that particular point. That means potential difference basically means potential drop between 2 points, VA and VB. Okay, VB. So this is the potential difference between 2 points, A and B. But if you have another point which is infinity, okay, infinity. So infinity is another point. Okay, so infinity, the voltage will be, potential is V infinity. So potential difference between V infinity and B is B infinity, but generally we write potential at B. That means whenever you are finding the potential at a particular point, you are actually comparing with respect to infinity. Okay, but potential difference between, you are comparing between one point to another point, because it is very simple. If you have a charge at A, if you drag that charge and bring to B, that means you are doing the work done, okay, against the field. So that is the potential difference between A and B. But if you drag a charge from infinity and bring it to B, that means you are doing the same thing. You are dragging the charge from infinity to B. So it is potential difference between infinity and B. But generally we call that potential at that point B. Okay. So the same thing, it is the potential at that point B. So it is infinity to that particular point. Okay. Because it is not A to B, it is infinity to R, that distance. Okay. So taking that concept which we have discussed, so that is why we have written that V is equals to E dot dl, integration of E dot dl. Now whenever you are doing VAB, that means it is very simple, that VAB is equals to A to B E dot dl. Okay, E dot dl or minus E dot dl, and VBA will be infinity. So this won't be minus, this will be plus E dot dl. Now if you are adding them, so what you are doing actually, you are doing the closed line integral. So that means integration, if I add them, add these two equations, if I add these two equations, equation 1 and 2, so what is happening in the LHS, we can get 0. In the LHS we are getting 0. VA plus VAB is 0. In the RHS, what we are getting AB E dot dl plus BA E dot dl. Okay, so that is basically the traveling from A to B and B to A. So it is closed line integral of E dot dl. Okay, so that means it shows that the potential difference in a closed path is actually 0. This is the conclusion, that if you find the potential difference in a closed path, it is actually equals to 0. This is very similar to what you have studied in physics, that work done in a closed path is 0. That means if you are starting from a point A, you are traveling a distance and you are coming back to the same point A, that means your displacement is 0. If you can remember, your school you have studied. So displacement is 0 means you have not done the work done is 0. Okay, The same thing here, the potential difference along a closed path is 0. That means implies that no net work done is done in moving a charge along a closed path in an electrostatic field. In an electrostatic field, no work done is done. Okay. Now, if you can see, if we have this equation number 14 with us. Now applying Stokes theorem. Stokes theorem means transform the closure integral to a surface integral. That is, closure integral of E dot dl, E is a vector, is equals to surface integral of curl of E, that is equals to 0. So if you compare these two equations, we can write curl of E is 0. Okay. So that means this implies, if you can remember, a vector whose curl is 0 is called irrotational or conservative vector. If you can remember, we have studied this. So it is a irrotational vector. So curl is 0. Thus an electrostatic field is a conservative field or an irrotational field. That means electrostatic field E has curl 0. This is a law. Okay. This is very important. So electrostatic field is having curl 0. Okay. So this is the second Maxwell's equation. Okay. So first Maxwell's equation we have seen previously, that this equation, I think it is in this slide, no, or not over here, in Gauss law. Okay. That is the divergence of E. The divergence of rho v is 0. If you can remember, divergence of volume charge density is 0, which we have obtained from the that Gauss law. Okay. Now from the way we find potential V, okay, it follows that there is what we can, okay, so this is the, you can say this is the derivative form. Okay, so this is one equation which we have got, that is the curl of E is 0. Now we want to directly find the relationship, because we have a relationship between V and E. Okay, this relationship we have, that V potential difference between VAB is equals to line integral minus line integral of E dot dl. Okay, this we know. This is the integral form. Now in vector differential form, we can represent in this way, that this is the integral form we know, the V equals to line integral of E dot dl, it follows. Now if you find the derivative, suppose to differentiate both the terms, LHS and RHS, what we can write? We can write dV, derivative, equals to, integration sign will be gone, so minus E dot dl. Okay, so E dot dl, so what does it mean? What is E dot dl? E dot dl means E is a vector. E is a vector, isn't it? E is a vector of electrostatic field. So in Cartesian coordinate system, it is written like this: Ex unit vector x plus Ey unit vector y plus Ez unit vector z. And what is dl? Dl is the displacement. Okay, that is, dl will be, it is actually dx unit vector x plus dy unit vector y plus dz unit vector z. Now if you do the dot product between them, what result you will get? According to the unit vectors, okay, the corresponding unit vector will be, you have to do the dot product. So it is Ex unit vector, Ex dx, Ey dy plus Ez dz. So there is a minus sign in before, so it is minus Ex dx minus Ey dy minus Ez dz. That you are getting. Okay, but if you find the potential, okay, potential dV, okay, dV potential if you take, so the dV potential can be written like this: the partial derivative, okay, for dV dx into x dx plus del v del y into dy plus del v del z into dz. You can write in this form, okay, dV, because it is a scalar, okay, derivative of a scalar with respect to any parameter, because you can see it is not dV by dl, it is only dV. Since it is dV, so it can be represented in partial derivative form. Okay, and if you compare these two equations, what we can see that if you isolate dx, dy and dz, so we can write minus ex equals to del x of v, or es equals to minus del x of v, ey is equals to minus del y of v, and ez is equals to minus del z of v. Okay, as if this is the gradient of v, as if this is the gradient of v. Why? Because ex, because if you compare this equation, suppose in this equation ex unit vector x, okay, plus ey unit vector y plus ez unit vector z, you have this equation with you. Now if you take this equation and if you replace this, okay, what we have got, what you write? You write del v, okay, minus del y minus del z of v. That means in place of e you are writing this, in place of ey you are writing this, in place of ez you are writing this. सिर्फ ये वाला टर्म ही एक्सचेंज हो रहा है, ठीक है, ये वाला टर्म, this term is exchanging. So unit vector x will remain as it is, unit vector y will remain as it is, unit vector z will remain as it is. It is not changing. So you are just replacing ex with del minus del x of v, and so on. If you write this, if you concentrate on this particular equation, what you get? It is minus, if you take the minus sign ahead before, so what you are writing actually in bracket, what you are getting? You are getting del x of unit vector x, okay, that is this one, v plus x plus y, which is nothing but equals to gradient of v, isn't it? Gradient का equation है, is equals to gradient. So we can conclude that electric field intensity in vector form can be written as the minus of gradient of v. That means v is a scalar quantity. If v is a scalar quantity, so if you take the gradient of v, that means gradient of a scalar, it becomes a vector. So electrostatic field or electric field intensity is a vector which is equals to minus of gradient of the scalar vector, scalar field, the scalar quantity potential. Okay, 1 second. Okay, so electric field intensity is equals to minus of gradient of potential. So these are the two equations, that is, this is the relationship between E and V. Okay, so V in integral form it is equals to this, okay, and in derivative form it is equals to this. That means the relationship between E and V, there are two relations in integral form and derivative form, because in integral form what we are doing, we are finding V from E, that is E is a vector, so E dot product with dl, line integral actually, which is the dot product, we are getting, converting the vector into scalar. Here we want to find out E from V, so this is a relationship between E and V in both terms. Okay, so the negative sign shows that the direction of E is opposite the direction of V, in which V increases actually. So E is directed from a higher level to lower level of V. That means we have already seen that whenever you are traveling a point from A to B, shifting a point from A to B against the electric field, okay, that means the potential will be applied in the opposite direction. So we are doing the work done against the field. So work done against the field means the potential is in the opposite direction. So potential is actually the work done per unit charge. Okay. So since the curl of gradient of a scalar is always 0, that we have already seen this equation. Okay, the curl of gradient of a scalar is always 0. So equation 15, okay, which we have seen over here, equation 15 obviously implies over here, okay, implies that E must be a gradient of some scalar function. So E must be a gradient of some scalar function, because if you can remember in the Maxwell's equation, this we have seen that curl of E is 0. So E electrostatic field is irrotational. Okay, and here we have seen that E is equals to gradient of V. So obviously now we can match that if curl of E is equals to curl of minus gradient of V, so it is 0. Okay, that is why it is 0. Okay, so hence we can also conclude that from the first equation, the curl of E is 0, that we have seen that the potential along a closed path is 0. From there we have derived that curl of E is 0, so electrostatic field is irrotational. So which means if a vector whose curl is 0, that means that vector is made up of some gradient of a scalar. If you can remember in the divergence and curl, that wave, four figures we have seen that are irrotational, that means a curl 0 vector means it is made up of a gradient of a scalar. That is why it must be a gradient of a scalar. So now we have proved that yes, E is a gradient of potential. That is why the curl is 0. Okay, because this is a law that curl of gradient of V is 0. If you can take any gradient, any scalar, if you find the gradient and if you find the curl, it will always become 0. If you perform this at home using a copy, you will see always it is coming 0. So this is the reason why curl of E is 0. Okay, so there is some numericals. Okay, so if you see this numerical over here, so 2 point charges minus 4 microcoulomb and 5 microcoulomb are located at point 2 minus 1 3 and 0 4 minus 2. So these 2 point charges are there, which are located in 2 separate points in a Cartesian coordinate system. Find the potential at another point, that is the 1 0 1, assuming 0 potential in infinity. So to find the potential at that particular point, okay, now the potential at that particular point, which means that this is actually the superposition theorem kind of thing, that in a space, okay, in a space there are 2 points. Okay, point number 1, sorry, this is okay, so this is point number 1, this is point number 2, so 2 points are there, and this is the third point. Okay, so this is the third point. Now in point number 1 we have a charge q1, we have a charge q1 over here. Point number 2 we have a charge q2. Okay, so now these 2 charges are there. Now we know the distance between them. How? Because since these charges are in the Cartesian coordinate system. Okay, so suppose this is the Cartesian coordinate system. Okay, x y z plane, and this square rectangle which I have drawn is actually, suppose, the electric field created by both the charges, because both the charges are creating an electric field and this point is within the electric field. So the potential at this particular point will be due to the effect of both the charges, because potential at that point 3 is due to the charge, potential at that point 3 is due to the effect of charge q1. So q1 will create a potential at this point, q2 will also create a potential at this point. Okay, so both q1 and q2 will create a potential at this point. So this is, suppose suppose this is one distance. Okay, distance between q1 and q2 is not required. Okay, so what we can do, first we will draw a line here. Okay, this is line. Okay, so to measure the distance, so this is r, suppose, and this distance is r1. Okay, and one second. Okay. Now this distance is r2. Okay, so what we don't know these two distances. These two distances are not known to us. So if I represent in a separate line, separate color, that will be easier for you to understand. If I draw with a green line like this, green color. Okay, this distance and this distance. So this is one distance, this is one distance. So what we are trying to do here, over here, we can see that 2 points q1 and q2. Now concentrate on q1 and this point 3. Okay, now distance from origin, that is the reference point, or the distance from a reference point or the origin of the Cartesian coordinate system, from origin to point 3 is r, and direction is in this direction. Okay, upwards towards 3. Distance from origin to q1 is r1, direction is towards q1. So what is the distance between q1 and 3, that is point 1 to point 3? What is the distance? Because we can measure this distance. How? Because we have the coordinates. Since we have the coordinates, we know what is point 1 and what is point 3 and what is point 2. So we have to measure distance between 1 and 3. We don't have to measure, we can calculate. Because if we have the value of r1 and r, we can calculate this. So this is not equals to r actually. This is not equals to r. What will be this? This depends upon the vector addition. Because see, this vector plus this vector will give you this vector resultant, isn't it? If this is a vector and this is another vector, so this is the resultant vector. Suppose a and b, vector a and b, so this is equals to a plus b, this vector. Now suppose you have a vector like this a, and you have a vector like this c. So what is this? Obviously a plus b is equals to c. Okay, forget this previous one, forget this one. So a plus b is equals to c. This is known to us, that c is equals to a plus b. But that means, so this is actually a plus b. Okay, now in C also, in C term also we can write this. Suppose I tell you that no, we have to write in term of C. Other way, how can we write? So this term is actually, so B, okay, so B is also written as C minus A. This is nothing but C minus A. We can also write this, isn't it? That means A plus C minus A will give you C. Here also R1 plus something is equals to R. So this one is R1 plus R minus R1 will give you R. That means we can write over here, this distance is R minus R1. Can we write? Isn't it? R1 plus R minus R1 equals to R. Same thing for this point 2, this distance is R2, this is R. So this distance from 1 to 3, distance between 2 to 3, distance between point 2 to point 3 will be how much? Since distance from 0 to 2 is R2, so from 0 to 3, origin to 3 is R, this will be R minus R2. So using this concept, okay, using this concept, we can write that, so this is the distance we are getting. So now we will concentrate on finding the potential. So potential at point 3 will be potential at due to charge q1 first, plus potential due to charge Q3, and if there are n number of charges, so the potential due to all the charges at that particular point will be calculated, calculated and then added to find the total potential. So it is a cumulative. Okay, so potential at this particular point will be potential due to charge Q1. So it is Q1 by 4 pi epsilon naught, and the distance is r minus r1, this distance, plus Q2 by 4 pi epsilon naught into r minus r2. Okay, plus due to infinity. Okay, so at infinity is 0, so not required. Now Q1 is given minus 4 microcoulomb, Q2 is 5 microcoulomb. Okay, now you have to find the distance between r minus r1 mod of r minus r1 plus mod of r minus r2. You have to find the potential, so you have to find the scalar, so only magnitude will do. So how they are doing this, you cannot write in this way. So what we can do, we know very easily that r minus r1 means r is what? R is this distance, isn't it? Distance from 0 to 1. Very easy. In basic, actually in school level you have done. So origin, what is the value of origin? 0, 0, 0. And what is the value of 1.1? It is 2 minus 1, 3. If you find R1 is nothing but 1 minus 0. इसका जो distance है वो distance मतलब 2. Okay, this distance. Okay, oh sorry, yes, the distance will be this. Distance is this one, 2 minus 1, 3. Quite easy. What is R? R is this 1, 0, 1. So R minus R1 will be same. This, the difference between these two. Difference between these two. So this is nothing but, if you write 2 minus 1, 3, so R is a vector, R is a displacement. So you cannot write 2 minus 3. This is for shortcut they have written. This is actually what? This is actually 2 unit vector x minus unit vector y plus 3 unit vector z. और R क्या है? R है unit vector x plus 0 plus minus unit vector z. If you subtract them, okay, if you subtract them actually, so what you are getting? Oh sorry, not minus, 1, so this is plus. So you are subtracting, so you are getting minus unit vector x, minus 1 unit vector x, you are subtracting. This is r, this is r1, subtracting, and this is unit vector y, प्लस हो जाएगा, माइनस माइनस प्लस हो जाएगा, और ये माइनस होगा, तो माइनस 2 यूनिट वेक्टर z. So what you are getting minus 1, 1, minus 2. Okay, so you are actually getting this. This implies that this is this, but this is actually the vector. So minus unit vector x plus unit vector y minus unit vector z, 2z, is the vector r minus r1 vector. So what is the mod value? Mod value will be root over of minus 1 whole square plus 1 whole square plus 2 whole square. আরে বলে দিচ্ছি, আমি লেট শুরু করেছি তো। Okay, so this is 1, 1 and 4. So it is a root over of 6. Same way it will be done for r minus r2. Okay, then you put the values and you get this value solution. This is the potential at that point. Okay, you can see it is in kilovolt. Okay, so this is another problem. So I will continue this problem in the next class. Okay, because it is already time.